in this example, we want to find all the fourth roots of this complex number. And again, we want to write our answers eventually in rectangular form. Since we're finding fourth roots, there are going to be 4 answers. Remember, if I was raising this complex number to the 4th power, there would only be 1 answer. When you raise a complex number to a power, you get 1 answer. When you take the root, then you have however many roots your root is, like 4th root would be 4 answers. That's critical to recognize in the first step, and that's usually what people miss. So let's rewrite our number in rectangular form. Let's rewrite it into polar form, and rather than go through the steps on this one, let's use our calculator to do that. So we said that if we need to find the polar form, we need an R and we need a new theta, so we can go to the catalog and we can pick out RPR and then type in the real part and then comma and then the imaginary part, 8 square root of 3 without the I, and that gives us an R value of 16. And then if we go back to the catalog and pick out the RP theta and type in the same real part, comma, imaginary part, then we get an angle of 120. So rewriting this number, this complex number in trig form is going to be 16 CIS 120 degrees, and that's the number that I'm working with. That's what I want the 4th root of. So there are 2 pieces of information that I need. The first piece is the R, and the R is easy to find. You take the 4th root of 16 to get the new R value, and that's going to be 2. Then you take your theta of 120 degrees and you add to that every coterminal angle, so 360 degrees times k, where k is an integer. Since we're finding a 4th root, we want to divide each part of that expression by 4. 120 divided by 4 is 30 degrees. 360 divided by 4 is 90 degrees. And then we have times k. So this expression is going to give me all of my angles that I need for my answer. So my first theta is when k is 0. If k is 0, then it's 30 plus 0, which is 30 degrees. My next theta is if k is 1. If k is 1, then I have 30 degrees plus 90 degrees, which is 120. Now you can see that as k increases by 1 every time, I'm just adding 90 degrees to my angle every time. So I don't have to go through the process of substituting in a 3 for k. I can just take my 120 and add 90 to it, and I get 210. And then 210 plus 90 is 300. So those are the angles for my answer. This all goes back to the fact that our vectors are going to be equally spaced. Okay, so once you do the 360 divided by 4, or whatever your root is, then you know what you're adding to each vector to get to the next angle. All right, so we have all of the information to write the polar form of our answers, and I like to go ahead and write them out so that I don't get lost in this whole process. So 2 CIS 30, and then 2 CIS 120, 2 CIS 210, and 2 CIS 300. Let's take a look at the graph of that real quick. If you graph these when they're in polar form, that's really easy to do. The length of each vector is just 2. So I have a circle here that indicates the boundary for the vectors. They're all the same length. And then you can see that my first angle is 30 degrees. And then my next angle is going to be at 120 degrees. So this angle between them right here is the 90 degrees. Notice that your vectors are equally spaced. When you're choosing the answer choice from multiple choice of your vectors, it's always going to be the vectors that are equally spaced. You have to have as many vectors as whatever your root is, and also your R value needs to be the length of the vector. But those graphs are pretty easy once you learn how to recognize them. They're really easy to pick out of multiple choice options. Now the only thing we have left here is to change these roots to the rectangular form. So just a quick reminder of how to do that. It's very important that you determine the sign, plus or minus sign, of each of your values, and that you use the correct reference angle. If we're in quadrant 1 for 30 degrees, then everything's going to be positive there. So I'm just evaluating cosine 30 degrees, which is square root of 3 over 2, using the hand trick, plus I sine 30 degrees, which is 1/2. And then if I simplify that answer, I'm going to have square root of 3 plus I. Then I go to my next root, and I have 2 times cosine 120. Now this time I need to remember that 120 is in quadrant 2, and the reference angle is 180 minus 120, which leaves me this reference angle of 60 right here. And notice that's different than the 30 that we used in the previous root. So I have a cosine that's going to be negative in quadrant 2, and the value is going to be 1/2. The sine is going to be positive, so plus I sine of 120 is going to be positive square root of 3 over 2. And then simplify by distributing the 2, minus 1 plus I square root of 3. When we're looking at 210 degrees, then we are in quadrant 3, where the cosine and the sine are negative. And the reference angle is 210 minus 180, in this case 30 degrees. So we're back to that 30-degree angle. And the cosine and the sine are both negative, so cosine 30 is going to be square root of 3 over 2. And then minus I sine of 30 is 1/2. So negative square root of 3 minus I. And then one more. 2 times cosine 300. 300 is quadrant 4. The cosine is going to be positive. The sine is going to be negative there. So the reference angle is 60. This angle right here is 60, which is 360 minus 300 leaves you 60. And the cosine is going to be positive 1/2. And the sine is negative square root of 3 over 2. Simplify that one. 1 minus I square root of 3. And I think I didn't make any mistakes there. Those are your answers in rectangular form. Notice that you have 4 roots because we were finding the 4th root of that complex number. If I were to graph these angles or graph these complex numbers in their rectangular form, then they would correspond exactly with the vectors that I graphed in from the trig form. For instance, we'll just go through the first one. If I looked at the square root of 3 plus I would go square root of 3 on the real axis, and I would go 1 in the imaginary direction, and that would be that vector right there.